part of Emulsion's Instability and Formulation Issues and Challenges seminar. The first part we had earlier this month. I'm Yorinda Null. I'm the current COSCHEM president, and I'm also the sales and marketing manager at Vantage. And it's with great pleasure that I would love to introduce you to John this morning. Just before we do start, just a couple of house rules. We are recording this session. John also said that we can share the recording with you, not the PDF, but the recording is, he said we can share that with you. And then also, if you guys can just keep yourselves muted throughout. However, John also said that if you do have a question at that moment that it is on a certain slide, please feel free to unmute yourself and ask the question. He just wants it to be more interactive. If you do have a question while he is on a certain topic, then you can just ask. But yeah, then I'm going to give the floor over to John. He is from Cosmetic Solutions, and he is going to take us through emulsion stability and instability. Welcome, John, and thank you for being here and giving us some of your time.
Thanks, Yorinda. It's a pleasure. Thanks, Bridget. Thanks, Yorinda, for the lovely introduction, and good morning, everybody. Welcome to this session. I know your time is valuable. We're all very, very busy these days, so I hope to make it worth your while. It is a long session. We've allowed 3 hours for this. I don't think we'll need the 3 hours, but I also don't want to rush through this too quickly, because there's quite a lot of information here for you to take in. I think, as Yorinda said, if you want to ask some questions, I can't see the chat box, but I'm sure that Bridget and Yorinda can, or if you want to unmute yourself and ask a question, because sometimes it's better to answer that question when the slide's in front of us and we can all see exactly what the question is relevant to. So welcome once again. I think my introduction was complete, but I got my own business called Cosmetic Solutions. It's now 30 years old, actually, this year, and we specialize in a lot of services to the cosmetic industry, and one of them being formulation of emulsions. So that's why I thought it was very relevant to present this to you this morning. So without further ado, let's kick on, and let's hope we can all see the screen and everything is moving as it should. So let's start off very simply with what's an emulsion. And that's the definition. I'm not going to read it to you, but I think there are two important factors here, really. One is it's a multi-phase system with 2 or more phases. We always talk about emulsions generally and simplistically having 2 phases, an oil phase and a water phase. Often there are more phases in an emulsion, in what we call complex emulsion systems. We won't be covering those this morning. It's a little bit too complex, I think, for a general audience. And the important thing is, the important thing is that those 2 phases are either partially miscible or immiscible liquids. And if they're not partially miscible or immiscible, then we can't form an emulsion. We just have a homogeneous system. And the other important thing is that in an emulsion, the one phase, whether it be oil or water, is dispersed in the other phase, which is either oil or water, the opposite, of course, in the form of very fine droplets. And we'll look at the importance of those droplets and what they look like, and how the size of those droplets is important to the stability of the emulsion as we go through the presentation this morning. So that's basically the definition of an emulsion. If we look at a simple emulsion system, that's basically how it looks. So we have a very, very simple, this is an oil and water system. The so-called dispersed phase is the oil in the yellow there. So that's an oil droplet in yellow, that's called the dispersed phase. And the surrounding phase in red is called the continuous phase. In this case, it would be water. So for an oil in water emulsion, we have oil dispersed in water. If it were a water and oil emulsion, which is the other type we can encounter, then it would be water droplets dispersed in oil, in an oil phase, or continuous phase. So you would have red droplets inside a yellow box, basically. And that's basically what a simple oil and water emulsion system looks like. Now, this is the first important thing, I think, to address when we're looking at creating an emulsion system. And I think the one thing that we sometimes tend to forget is what we're talking about with an emulsion system is a thermodynamically unstable system. So what we're doing, we're taking two perfectly stable phases, an oil phase and a water phase, and we're trying to get them to interact with each other to form an emulsion. And in so doing, we are actually increasing the thermodynamic energy, the free energy of the system. Now, I think most of us will know from our matric days that if we've got a high energy system, then everything will happen to try to reduce that energy. So in other words, if we've got a very high thermodynamic energy, then what will happen is that things will take place within that system to try to reduce that energy level, because there is one of the basic laws of physics is that things will reduce to the most basic or lowest energy state. So if we look at what's happening when we create our emulsion, we've got basically two phases, as I've said, an oil phase and a water phase. And we are applying some energy in the form of mechanical agitation. Now, it is possible to create an emulsion without any mechanical agitation under certain conditions and certain types of emulsion, but generally speaking, for I would say 95 or more percent, 98% probably, of the emulsions that you're going to be forming in your lab or in your factory, you're going to need some sort of mechanical agitation. Now that is a very important step, because that's where the energy is coming from. That's where the energy comes from to form the emulsion. Because remember that little dispersed system at the top of the page there, the yellow droplets in the water phase, the red water phase, that is considerably higher energy level, if you look at the graph on the left-hand side, than what we started with. So that particular system is unstable. And all we've done is apply mechanical energy to it to create that system. As soon as we stop the mechanical energy, as soon as we stop providing that, then what is going to happen is that system is going to be at a high energy level without any input to keep it there. Now, at that stage, where does the energy go to? Well, it goes into what we call the interfacial area. So if you look at the starting point, bottom left, the interfacial area is simply the area defined by the area of the beaker at a single phase, where the oil phase and the water phase meet. If we look at the top center, we can see that the interfacial energy or interfacial area is increased many, many, many thousands of times, because every droplet now is an interface with the surrounding water phase. So that's where the energy goes to. So it's provided by the mechanical agitation, and it actually is present in the emulsion system as interfacial energy because of the interfacial area increase. Now that particular system is now unstable, and in fact, if we just leave it over time, and that time can be anything from probably less than a minute right through to several hours, we will go back to where we started effectively. So we'll end up with an oil phase and a water phase, with the oil phase sitting on top of the water phase. And that's what will happen if we do nothing else, if we just remove the mechanical energy. What we need to do, of course, is we need to make sure that, that central box, that illustration at the top, becomes stable. And the way that we do that is we add an emulsifier. And when we add an emulsifier, and we'll see why that is in a moment, when we add that emulsifier, then we retain the structure of the system, but we reduce the energy levels considerably. So in other words, what happens is the addition of the emulsifier reduces the interfacial tension and the interfacial energy. And that's how we get a stable emulsion. And that's why most emulsions, in fact, nearly all emulsions, are not perfectly stable states. You know, most emulsions, given enough time, will actually separate in the end. Either separate, or they'll become unstable through oswald ripening or creaming or sedimentation. We'll look at those in a moment. So an emulsion is a metastable situation. It's a metastable condition. It's not perfectly stable. There are perfectly stable emulsions, but they are special cases, and we're not going to cover those this morning. But so any emulsion you create in your laboratory or in your factory will eventually become unstable. The question is for us as cosmetic scientists and developers is, can we make it stable enough so that it services the consumer in the way that it should? So the current regulations state that a product must have a shelf life of 30 months in South Africa. under normal conditions of use and storage. And what we do is we conduct things called stability tests, and we'll look at those later, to decide whether or not our emulsion we formed is going to fulfill that requirement of 30 months stability in the consumer's hands. If it's not, then obviously we have to think very carefully about either things like sell-by dates or best before dates, and other things as well. We'll come on to that in a moment. So basically all we're doing is we're adding an emulsifier or an emulsifier system, because you very rarely add one material, you have more than one, to take a metastable system and make it stable by reducing the interfacial tension of the system itself. So that's basically, in a nutshell, exactly what creating an emulsion looks like. Okay, so let's just summarize what we've looked at so far then. So basically, we know that emulsions are thermodynamically unstable systems, and that's pretty much true for 98% of emulsions that we're going to encounter. I have to say that over the years, I've been doing this for a long time now, more years than I care to remember, actually. And the emulsion technology, since I started in 1984, has come on leaps and bounds, and some of the newer emulsifier systems that are available now are just really efficient, and we'll see why that is later on. We'll talk about mixed emulsifier systems and why they're so good, but emulsions are nevertheless thermodynamically unstable systems. The degree of instability, as I said, is linked to the change in interfacial area, because interfacial area creates interfacial energy, interfacial tension, and basically it's a function of the area itself. So the change in energy delta S is directly proportional to the amount of new area created as we form the emulsion system. Remember, we need to use mechanical energy to form it in the first place, and when mechanical energy is provided, we get this massive increase in interfacial area, and that's what provides the emulsion, but also is responsible for the instability of the system. So in the majority of cases, I said 98%, we do need agitation. The type of agitation is very important. We'll see later on why that's so, because we want to make sure that we create an emulsion that is going to deliver not just the physicochemical qualities we need, but also what the consumer experience is going to be, because things like, for example, particle size, and I meet many formulators in the industry. When you talk about particle size, they don't really know what the particle size of their emulsions are, and that's not a good place to be, because your particle size of your emulsion is going to be directly correlated with the consumer experience, and depending on the emulsion system, you'll find that a certain particle size range will give you a product which gives you a different experience on the skin or the hair or the body, depending on what the product is, of course. So we do need to know a little bit more about particle size and how that's related to stability and how it's related to the consumer experience. I'm not going to cover the consumer experience today. It's another topic completely, but I will talk about particle size, how we determine that, and how that's linked to emulsion stability and commercial viability. It's going to be an important part of the discussion this morning. And then, as I said, just to recap on the last slide, the way that we stabilize an emulsion, a metastable emulsion, is we actually apply or use an emulsifier system. And what that does, that orientates itself at the interface. The emulsifiers will always be found at the interface, and that's how they reduce the interfacial energy or interfacial tension, because they effectively cross the interface of the emulsion, and in so doing, they bridge the interfacial energy gap, and therefore reduce the interfacial energy and stabilize the emulsion system. But remember, as I said a few months ago, every emulsion is metastable. Every emulsion, apart from very few, will, given enough time, separate. We just want to make sure that it doesn't separate in the consumer's hands, because that's not a very good way to impress our consumers about our new launches when they start to separate. Be very wary of any products in the shops or the shelves where it says shape before use, because that probably means the emulsion is not stable. I've seen that happen with some big companies actually, where their product is found to be unstable. So what they've done, they put shape before use on the on the pack. And interestingly enough, there's a very, very well-known brand of French mustard which is sold in South Africa. Delicious French mustard, by the way, but it's unstable. It's always been unstable. It's never been stable. And it's interesting that no one seems to complain about it because the taste is so good. So you can get away with it sometimes. Okay, so let's move on then. We've basically introduced emulsion systems, talked about the way in which they're created, and I now want to get into a bit more detail about the energy of the system. We're talking about these energy levels, what factors are involved here, apart from the interfacial area, and to take a little bit more of a look on 3 different types of energy which are associated with instability, and see what their contributions are. Because if we look at the contributions of all these 3 different types of consideration, they all have a role to play, and they all determine what the extrinsic factors are going to make our emulsions stable or unstable. And obviously we're looking for the most stable systems that we can create. Interestingly enough, as an aside, sometimes we want to create an emulsion which is not absolutely stable. For example, if we want a skincare product to have what's called a breaking oil phase, in other words, we want the product to be stable in the bottle or stable in the jar, but when we actually apply it to the skin, we want it to break quickly so that we get better characteristics, application characteristics on the skin. That's not something we're going to cover in detail today, but that's a situation then when we try to create a better stable system, which is stable enough, as I said, to be commercially stored, but has got the right stability profile to break on the skin to give the right consumer experience when the consumer uses the product. So that's a different challenge, quite a tricky one actually, but it can be done. But that's a case when we don't want necessarily the most stable emulsion. We want something to be a little less stable for the consumer experience. Okay, so let's look at the first factor. This is something called Brownian motion. And Brownian motion basically describes the movement of a small particle within a continuum. The movement, the little particle there in yellow, the movement is random. It's not a straight vector. So what we do, and when we're looking at describing this mathematically, we apply a vector analysis to it. So we actually take our random movement. You can see with the squiggly arrow, and we apply a vector to that, which we've got the line D there, and then we can actually describe the mathematical description of this movement is given by that equation. Now, I don't want you to get too worried about mathematics. I'm sure you've all done enough of that in your lives already at matric, and unless you're a mathematician by training and trade. And I always find that I've got a very good friend who's a brilliant mathematician, and he talks about mathematic models in everything in life. You know, whatever you're talking about, he finds a mathematical model for it. So if you're going to go and buy a new car, there's a mathematical model for doing that. So it's quite an interesting, but a very unusual type of person. But a nice guy, but everything is math. But don't worry too much about the math. But let's just look at the terms here. So D is what we call the diffusion coefficient, and this is the vector, if you like, that describes the Brownian motion contribution in an emulsion system. The reason why this is relevant, by the way, is because the internal phase or dispersed phase of an emulsion is responsible, or partly responsible, for stability or instability, and we'll see why in a moment. So therefore, we need to look at its movement to see how this is going to affect the stability of the emulsion system. So D is the diffusion coefficient. K is something called the Boltzmann constant. T is the temperature in degrees Kelvin. So that's the first observation. Okay, we want D to be small because one of the requirements for emulsion instability is for the dispersed phase droplets to collide. If they don't collide, they can't coalesce. If they can't coalesce, then you've got less chance of an emulsion becoming unstable. It can still cream, and creaming is different to coalescence, and we'll look at that in a moment. But if you can avoid coalescence, then you've got a good way to stabilize your system. Now, to reduce coalescence, we want D to be as small as possible. In other words, we don't want the internal phase droplets to travel very far, because if they don't travel very far, they're not going to be able to coalesce easily with their neighbours. So D to be small. Now, for D to be small, we need the top line of that equation to be small. And that means that temperature, or the temperature in degrees Kelvin, needs to be low. So one of the first golden rules for emulsion instability is that, typically speaking, the lower the temperature, the more stable your emulsion will be. Okay, so in other words, and that can be good news and bad news. So if you've got an emulsion, for example, which is stable at room temperature, if you were to put that into an oven at 40 degrees centigrade, you may find, surprise, surprise, that after a few days or a few weeks, your emulsion is no longer stable in the oven, but it's perfectly stable in room temperature. And that's why we use elevated temperatures when we do stability work with emulsions. We'll come on to that later on this morning. So the first thing to remember is that as the temperature increases, then the stability of your emulsion system will actually get worse. The exception here is, of course, is when you go below zero. And when you go below zero, then you've got to take into account the freezing of the water phase. And depending upon the freezing point of the water phase, it can be just below zero or quite considerably below zero. But when we freeze the water phase, then we start to destroy the emulsion system, particularly if it's an anionic system or a cationic system, then we will destroy it. And that's something called freeze-thaw stability, which not many companies in South Africa do. In fact, we don't do it as a matter of course, unless we know our client is going to be selling the product in a cold climate, because in South Africa, we don't really need to do freeze-thaw testing. It can be done for academic reasons. So in other words, if we want to find out more about the instability of our system, we can do a freeze-thaw test for academic reasons. But if we're a company that's supplying products to cold parts of the world, then freeze-thaw testing would be a very good idea to do, because for many emulsions, even a single freeze-thaw can cause problems. So we don't want that to be happening in the marketplace. So, but as a general rule of thumb, the higher the temperature, then the less stable the emulsion will be. Obviously, the other thing to look at is the viscosity of the continuous phase. That's on the bottom line of the equation. So that tells us if we want to keep D small, then the higher the viscosity of the continuous phase, the more stable our emulsion will be. Now, I think if you think about it from a common sense point of view, that makes sense, because if I've got a very viscous continuous phase, it means that my droplet can't move very quickly within that continuous phase. This is something which is overlooked by a lot of formulators. And when we're looking at viscosity, and we'll cover it very briefly later on, we've got to think about something called yield point. Because just to make something thicker, inverted commas, whatever that means, doesn't necessarily mean that we're going to make that emulsion more stable. What we want to try and do is we want to try and create a yield point. And a yield point is where you get a very, very high static viscosity in the absence of shear. And when you apply shear, then that static viscosity drops and becomes a dynamic viscosity, which is then quite low, which gives us good application characteristics on the skin. So we just need to make sure that we've got a yield point in our system. And, some modifiers, some rheological modifiers will do that for you. So, for example, if you want to create a yield point in an oil and water system, a really good way of doing that is xanthan gum. Xanthan's got a very, very good yield point, depending on the xanthan gum you're using. Now, not all xanthan gums are created equal, I can assure you. It does make me smile when we develop formulations. We use very high quality xanthan gums, and there's only a few around. They're very expensive, but they work. What then happens, most of our clients go off to contract manufacturers, and suddenly the formulation doesn't work anymore. It's unstable. So I get these rude complaints about the formulation's not stable. And we do a bit of investigation, and we find that the contract manufacturer is using a xanthan gum from China, which doesn't work. And surprise, surprise. So that's a very good example where you've got to be very, very fastidious. If you're formulating as a consultant like we do, or if you're formulating for your own company, do make sure that when you purchase your raw materials through your procurement department, you don't start changing the grades of the materials. I've heard it said that in some cases, the procurement department looks at the inky name, and if the inky name is the same, then it must be the same. Well, nothing can be further from the truth. And the reason I'm dwelling on this, and it's maybe digressing slightly, is that xanthan gum is a classic case. And we've had many cases of formulations that we've developed which are stable at 50 degrees centigrade for 3 months. And when they go into manufacture, they suddenly become unstable. We then get blamed for that, of course, being the formulator. And in every single case that I've investigated, the xanthan gum has been sourced out of a cheaper source, and very often the Far East, which is notoriously unreliable, although getting better. So that's something just to remember when you're formulating, and that whole transition from formulations into production. Please make sure you don't change your sources. When we formulate, we choose certain companies for a reason, because we know that their products, their ingredients work. And the last thing is the particle diameter. So, in other words, this is an interesting one, because this is actually a paradox here. Because if we look at the Brownian motion equation, it tells us that if we've got a larger particle, then we will have a lower value for D, and therefore a more stable system. It's actually not the case. In fact, in this case, the bigger the particle, the more unstable the emulsion will be. And the reason why that doesn't figure here is because the next two contributions I'm going to show you have an overriding effect over the Brownian motion contribution. So these three contributions I'm going to show you now, they all have a different role to play in emulsion stability. And the other two I'm going to show you now have a bigger overriding effect on the overall stability profile of the emulsion. So generally speaking, for a more stable system, you need a smaller particle size, a smaller dispersed phase particle size. Let's look then at the second one, and this is the London van der Waals forces, also very important. And this is a very simple equation, described, as you can see on the screen in front of you. And in this case, the VA, that is the London van der Waals forces of attraction. So this is an attractive force. This is a force which tends to make very, very small particles in a system come together. That's exactly what we don't want, of course, in an emulsion system, because we have these dispersed phase droplets that we want to try and keep them separate, because if they're separate, then no coalescence can take place. Unfortunately, van der Waals forces are acting against this wish. So we want to try and keep these low, of course. If the van der Waals forces of attraction are low, then the attractive force between adjacent droplets is going to be low, and therefore we won't get the attraction that's going to cause coalescence. A is something called the Hamaker constant. Little a is the radius of this dispersed phase droplet. Now, this is the first point to note. I said in the previous equation that the bigger the droplet diameter, the more stable the system would be, if we were to take that force contribution only. Here we can see we want to try and keep VA small. So here, because the radius is on the top line, we want to keep the radius of our dispersed phase droplets as small as possible. And that indeed is the overall case for maximum emulsion stability. So the smaller the droplet, whether we're measuring diameter or radius, it doesn't really matter. I mean, D equals 2R anyway. According to the van der Waals forces of contribution, we want to try and keep the dispersed phase droplet diameter or radius as small as possible. And H is the distance between the dispersed phase droplets. So in other words, we want to try to maximize the distance between adjacent droplets. That makes sense. I think if you're looking at a force of attraction and you're trying to prevent two droplets from coalescing, the bigger the distance they have to travel, the more likely is they won't do that. So what does this mean? It means that we need to think a bit about the density of our droplets in our emulsion system. So if, for example, we've got a very, very high percentage of oil phase, so if we're creating an oil and water emulsion where we've got, say, 40% oil, which can be done quite easily, then we need to make sure that we've got a higher level of emulsifier there to compensate for that creation of a larger number of dispersed phase droplets, because the more dispersed phase droplets we have, the closer they're going to be to each other, the higher the interfacial energy is going to be, and the more likelihood there's going to be of coalescence. So we need to make sure that we've got enough emulsifier there to actually satisfy the needs of that high energy system. But we don't want to put too much emulsifier in, because if we do that, then not only are we wasting money because we're putting an expensive material, often expensive material, into a system we don't need to. And some of you may have noticed that in some of your emulsion systems, you're getting something called soaping. So this is when you actually apply your product to the skin and it doesn't absorb very well and it starts to look a little bit like a shaving soap on your skin. And one of the reasons for that to happen, there are many reasons that can happen, but one of them to happen is you've got too much emulsifier. And I do see in the case of new formulators, people coming into the industry, and we all got to learn, of course, so this is not a criticism. I see a lot of young people's, young students, emulsions, they come to me for advice. And one of the mistakes they do make is the emulsifier levels are too high. I understand why they're doing that, because you think the more you've got, the more stable it's going to be. That is true, but there is a plateau point beyond which you won't increase stability. All you'll do is increase cost and reduce application characteristics and the aesthetics of the application characteristics. So, you know, the lovely thing about these equations that we're looking at now, and you could say, well, this is very abstract. It's not really very relevant to what I do for my everyday job. It does start to explain some of the things that we see in the real life situation when our consumers apply the products to their skins. So this is something else to bear in mind. The last one, and I always think, for me at least anyway, the most important one, and I think Mr. Stokes would agree on this, please remember it's Stokes apostrophe, not Stoke apostrophe S, okay? It's Stokes law. And this is really, this is the law that really determines the ability or inability of an emulsion to cream or sediment. Now, what do I mean by that? If we've got an oil and water emulsion, if you think about the relative densities of the two phases, typically the oil phase is going to be around about anything between 0.92 and 0.9899, but normally less than 1. There are exceptions to that. You can create oil phases with a density of greater than 1. It's quite difficult to do. Whereas your water phase is going to be at least 1, you know, because the density of water is 1. And if you put glycerine in there at a couple of percent, and propylene glycol at a couple of percent, and pentylene glycol, you'll find that suddenly your density of your continuous phase is maybe 1.1 or 1.005 or something like that. But the most important thing is that in an oil and water system, the oil phase is less dense than the water phase. Therefore, there will be a tendency under the forces of gravity for the oil droplets to rise in the system. Rise to the top of the system, and that is a process we call creaming, because we're forming a cream, and that's where those of you who still drink full cream milk, that's what's happening there. The full cream is an oil-rich phase due to the gravitational differences between the oil phase and the water phase. And you know, water and oil phase, we've got the water dispersed in oil. There, of course, the internal phase, dispersed phase, is heavier than the continuous phase, and the water droplets go to the bottom of the system, and that's called sedimentation. So it's either creaming for an oil and water system or sedimentation for a water and oil system. So it's always the movement of the internal phase or dispersed phase that determines whether it's creaming or sedimentation. So let's look at this equation more closely. V is the velocity of the dispersed phase droplet. Now, it stands to reason, I think, that if we're trying to arrive at a stable system, we don't want that velocity of that dispersed phase droplet to be high, because the more quickly it moves, then the more chances there are of a collision. So if I'm on the highway and I'm driving at 70 kilometers an hour, and the car in front of me stops quite quickly, I've got a better chance of not hitting the back of that car than if I was traveling at, for example, 150 kilometers an hour. So we want to try to keep our velocity of the dispersed phase droplet as low as possible. And how do we do that in accordance with this equation? Well, again, we see that the radius appears on the top of the equation. Therefore, if we're trying to keep V low, we must keep A low. And this is now why you can see that where we originally predicted that the higher diameter droplets will be more stable, the last two force contributions, we've seen now that the radius of the droplet or diameter of the droplet must be kept low for maximum stability, and this is confirmed by Stokes' law. PC is, or rho C, sorry, is the density of the continuous phase, and rho D is the density or SG of the dispersed phase, and eta is the viscosity of the continuous phase. So the takeouts from this equation are quite straightforward. We can't do much to change the force of gravity unless we go to the moon, of course. So if you're a formulator and you can't get it right here, then just call Musk, and maybe you can go to the next adventure to the moon and maybe do some formulation work there. It's a lot easier to create a stable emulsion at the moon than it is on planet Earth. But that's not a very practical solution, I'm afraid, unless you've got a few $1 million to spend. So G is gravitational force. A is the dispersed phase, the dispersed phase droplet radius. Try to keep that small, so small particle sizes. The smaller the particle size, the more stable our emulsion is going to be. Try to keep the densities of the oil phase and the water phase as close as you can. This is not very practical, to be honest with you, because these things are pretty much given. I don't know of any formulator that deliberately engineers this, because basically there are a number of reasons that you put an ingredient or a raw material into a formulation, but their density or SG is not one of them normally. So this is something you've got to be cognizant of if you do have a very light oil phase. So in other words, if you're using oils which have got a very, very low density or SG, they are going to be more difficult to stabilize in an emulsion system than an oil with a more conventional SG. So if you are using light oils, when I say light oils, I don't mean to apply on the skin. I mean light in the sense that they've got a low SG or a low density, then they are going to be more difficult to stabilize than the more conventional oils, for example. And then, of course, the important thing here, very important, is the viscosity of the continuous phase, eta. Again, as we saw with the last discussion, the higher the viscosity of the continuous phase, then the more stable our emulsion system is going to be. And again, it's about the yield value. Okay, yes, if we increase the viscosity, you will get an improvement in stability. I cited xanthan gum as a good example of a rheological modifier which is very effective at very low cost as well. I mean, xanthan gum will work effectively anything above 0.3% and sometimes less, but typically between 0.3 and 0.8 in a formulation, and give you a very, very nice yield point, which gives you very, very good stability and prevents creaming, of course. And that's the whole point of putting this rheological modifier in there, is to prevent creaming. So a rheological modifier doesn't do anything to your interfacial energy. It doesn't really affect that significantly. What it does do is stabilizes your system. So in any emulsion you create, you've got to have two basic components. One is the emulsifier system, which handles the reduction of the interfacial energy and the free energy in the system. And the second one is a rheological modifier that actually handles the creaming and sedimentation effects. So I do see sometimes emulsions without any rheological modifiers. The chances are they're not going to work unless they work by a different mechanism. If they work through liquid crystal stabilization, they will work. But there aren't that many emulsifiers that work through liquid crystal stabilization. There are a few out there. I'm not going to mention names because that's not what I want to do. But those of you who are associated with those materials will know about them. They do work well, but even if we're using those, we do use them quite a lot, we still add a little bit of a rheological modifier to our systems just to make sure we've got a belt and braces approach, particularly at high temperatures, because these effects, these creaming and sedimentation effects, will take place more quickly at higher temperatures, because obviously the velocity of the dispersed phase droplet is going to be higher, and we'll actually then more likely to get the creaming and sedimentation. So in as much, for example, that xanthan gum is a very, very good choice, not the only choice, there are plenty of choices, but xanthan gum is a good choice. If I was to use, for example, hydroxyethyl cellulose, which maybe, you might think, well, they're both, rheological modifiers, they both thicken the system. They do, but HEC does not produce a yield point. So whereas xanthan gum will produce a yield point, HEC won't. They're both pseudoplastic behavior, which is what we're looking for in our rheology. We're not going to cover rheology today too deeply. So something like HEC will not give you that yield point you're looking for, whereas xanthan gum will. So another good reason to choose different rheological modifiers. Sometimes we don't want a yield point. There are times when we don't want a yield point, in which case we may not use xanthan gum because that will give us a yield point we don't want. And that's obviously, part of the art of formulation. So formulation is 1/3 art, 1/3 science, and 1/3 cookery. So if you're a good chef and you can cook a good meal, you can probably formulate a good emulsion. Okay, so let's look then at the overall conditions for optimum emulsion stability. So low temperature, in general, gives you the most stable emulsion systems. A smaller dispersed phase particle size, droplet size, is the best condition for maximum emulsion stability, and the reduced density or low density difference between dispersed and continuous phases. We don't really have much control over the first one and the third one, because the temperature is going to be whatever temperature the consumer's at, or the storage temperature, or wherever our emulsion is going to be. And as I said a moment ago, it's very difficult to engineer low density differences by adding certain types of ingredients, and you very often will find you don't get the type of formulation you want. So the main factor that we have control over here is the dispersed phase particle size, and that we can control, and we can control it very well. And that's why it's so important. And when I talk to formulators and I ask them about their understanding of the dispersed phase particle size of their emulsion systems, and they don't even know what it is, that is a little bit of a concern. So it's not difficult to find out what it is, and it's not expensive to find out what it is. And we'll look at the end of the morning, we'll look at ways of doing that. So those are the most important overall conditions for optimum emulsion stability. And the last one is a high continuous phase viscosity, and we do have control of that. So we've got control over items 2 and 4 on that list. So when we're formulating, we need to bear those in mind. So keep the dispersed phase particle size as small as possible, and keep the continuous phase viscosity as high as possible. Now, again, just to repeat, when I say high, what we're looking for is a high yield value in general. And a yield value is a very, very high static viscosity, which is not determined by the consumer, because we don't want to create a high viscosity per se. For example, if I'm creating a facial moisturizer, and my external phase viscosity is akin to that of honey, I'm going to get a very unpleasant product. I don't think many ladies are going to enjoy the experience, or men even enjoy the experience of applying something to the skin when it's got the viscosity of honey to it. Okay, unless you've got something special like a massage gel or something like that. But generally speaking, for skincare, particularly these days, most consumers want their skincare to be fairly light, easily applied, easily absorbed, and more concerned about the post-application characteristics of the product. So items 2 and items 4 are the ones that we need to control in the formulation and manufacture of our emulsion systems. Bridget, I'm conscious that it's very quiet. I'm not sure if people are just overwhelmed or whether I'm losing them, but I assume no questions so far?
Yeah, and there hasn't been any questions yet.
Right.
I think somebody just asked for your email address, but that is about it.
Okay,
so I think
that's
everybody's
the easy
listening
one.
intently, making notes.
No, that's fine. As long as I'm not.
Any questions, guys, you're more than welcome to pose the questions. Like we said, there's never a silly question. Sometimes it's also good to refresh. We're all in the same boat at the end of the day, so it's good to go over this again and again. I mean, I've listened to this lecture with John loads of times, and I still, but I'm not scientific. I'm still confused. But thanks, John. Keep going.
Okay. Thanks, Bridget. Thanks. Okay. All right. Let's then look at emulsion instability and what are the symptoms of emulsion instability. Unfortunately, I think all of us are aware of these because in our day-to-day jobs as formulators, we unfortunately, I mean, I've been doing this many, many years, and Is every single one of my emulsions stable? No, it's not. I wish it was. And the hit rate's pretty good. I think we've got a hit rate of about 94% at the moment. So 94 out of 100 products we develop are stable first time out, which is not a bad hit rate, but I don't think many people get to 100 anyway. So let's look at some of the instability, signs of instability. So progressive changes in physical properties. A physical property, whatever it's going to be, pH, specific gravity, most often viscosity is the big one. It will change over time, and that's an indication that things are not as they should be. A gradual increase in dispersed phase particle size. Now, for most people, I would say the large majority of even the multinational companies don't routinely measure particle size as a function of stability testing. You can do that. I mean, obviously, it becomes a bit more expensive because it involves some sort of microscopy at the very least. And other than that, particle size analysis, which I'll talk about later on, because that would give us an early sign of something called Ostwald ripening. And Ostwald ripening is where we get a gradual expansion of the dispersed phase droplet due to the changes in the pressure, the internal pressure within the dispersed phase droplets. And that's to do with reorientation of the interface. So we don't often see Ostwald ripening very easily. When we see it is when it becomes coalescence, because when the droplets have become big enough, they coalesce, and then we'll see it as coalescence. And that will present itself in a number of different ways. So that's another thing that can really can cause problems with emulsion stability. A broadening of the dispersed phase particle size distribution curve. I'll explain what that means later on. This is why, it's particularly in difficult systems, it's very good to have information about your PSA, your particle size distribution curve, because it can give you a lot of information about your emulsion, what you do to fix it, that you can't determine from things like an ordinary viscometer. I mean, an ordinary viscometer, whether you're using a Brookfield or one of the counter types, I'm still a great believer in the old Brookfield. I think it's a fantastic device. Ours is now 23 years old and still going strong, and all the spindles are still straight in our case. I did visit a contract manufacturer a couple of years back to do an audit, and I won't tell you who it is. And they, most of you know that with most Brookfields, you get normally 7 spindles. They had 3 spindles, and 2 of them were bent. And I said, do you think you can get accurate readings on this? They just said, no, we just use the one that's not bent. So that's an interesting approach to viscosity determination. Quite how they do that in practice, I don't know, and I was afraid to ask, so I didn't progress that any further. I thought that's a discussion for another day. But the characteristics of the dispersed phase particle size curve is extremely important for emulsion stability. And then, of course, worst case scenario, full inversion, phase inversion, partial phase inversions, they're more likely to happen with water and oil systems. So inherently, it's more difficult to stabilize a water and oil emulsion than it is an oil and water emulsion. Having said that, when I started formulating cosmetic products, I think there were still some dinosaurs around, traipsing around the planet. But in those days, there were very, very few water and oil emulsifier systems around. You had very, very few. Probably I can count on the fingers of one hand. And they were very difficult to stabilize. It was almost like the universal panacea if you could stabilize a water and oil emulsion. These days, most of the big suppliers of emulsifier systems have got great products that they very often blends. It's almost impossible to stabilize a water and oil emulsion with a single emulsifier molecule. But some of the blends out there, and some of you may be working for those companies, you'll know what they are, and others of you will be using those products. It's much easier these days to get a good stable water and oil system, and there are certain reasons why you do that. There are reasons why you might want to create a water and oil system, mostly aligned to aesthetics and the efficacy of moisturization, because typically a water and oil emulsion will give a better moisturization characteristic through occlusion than an oil and water. That's a very simplistic statement, so don't take it as gospel. But that's the reasons you might want to do it. And they're not very popular in South Africa. But if you were to go to Germany, for example, in the German market, you'll find quite a high percentage of water in oil systems, because that market has just grown up with those types of products, and the German consumer quite likes them. So when you're doing any research of any type for your emulsion systems, please remember to test with your local market, or the market you're going to sell into, because your consumers do have different views around the world on what they prefer. What may be a very nice product in South Africa may not be so good in the Netherlands, for example, or America. So that's something we've got to watch out for. Creaming and sedimentation, I covered that in some detail just a couple of slides back. That's fairly obvious. You can see what's happening if you start to see the top of your emulsion becoming denser and more creamy. That's basically a creaming effect that you don't want. And then the horror of horrors, of course, is complete phase separation, and that's the last step in the instability of an emulsion system. So those are the things that we should look out for. Those are the symptoms of poor stability. And if we had an infinite amount of time, we could develop our emulsions and wait around for 3 years and just see if any of these things happen. I don't think many marketing departments would wait 3 years for new products. In fact, these days it's a miracle if they wait 3 weeks. But that's another topic for another day. So those, yes.
Sorry. There is a Letitia. I don't know if you want to unmute your microphone. I can see your hand is up.
Yes, my hand is up. Hi, John.
Thank you.
Hi.
Hi.
How are you? Good.
Good. Thanks, Letitia. Good.
So we are currently having this exact problem with creaming or sedimentation, and that is happening with a ringing gel. So what I found was that we can make a 5 kilo batch quite easily, but the minute we start scaling up, and we're having these issues. And I think there is a maximum of 7 ingredients in the formulation. What would cause that? So I'm not that involved in the production. We outsource most of our, all of our production is outsourced. So this is a third party, and this is the problem that we are currently facing. So how do you overcome that? So we make the 5 kilos, we scale to 10 kilos, then we make 100 kilos, and the batch bombs.
Okay, right. And what is the rheological modifier, Letitia, you're using?
So we're using Ceteris 25.
Okay.
And there's the ingredients. It's like Pig 50 shea butter. That is it.
Right.
That is what we're using. As I said, there's 7 ingredients: it's the water, the glycerine, preservative, fragrance, and polysorbate 20 as well.
Right. Okay. All right. So there's no rheological modifier there at all. So that's the first question mark. What we can do, I'm going to answer very briefly now. If you would like to send me, if you want to send me, we can sign an NDA. I can look at the formulation for you. But there are 2 things to say. Number one, there's no rheological modifier there at all. So it looks like you're relying upon the emulsifier system to give you the stability. Now, the reasons why, almost certainly, I'll be probably 100% sure of this. When you get CTRF 20 or 25 or something like that, then the way in which you process your shear rates are going to be absolutely critical in obtaining a stable system. If you don't have enough shear when you're actually forming that emulsion, you're going to get the wrong particle size, and you're not going to get the right crystalline structure in the emulsifier system. What is happening is, in the laboratory, I suspect you're using a high shear rotostator mixer to create that system. In your contracting company, I would bet a lot of money that they're not achieving the same shear rate as you are. That's due to several things. It can be due to the equipment they're using not being fit for purpose, and there are plenty of high shear mixers in the market. Unfortunately, there are copies of things like Silverson mixers that don't work. All they do is make a noise. It's a very expensive way to make a noise. Or that the equipment they're using is not sufficient for the volume of the product. So if they're making a ton, for example, that's a very different proposition to making 10 kilograms in the laboratory. So if they're making a ton, and they're using a top entry high shear mixing system. How do they know that all of that product has gone through that emulsifier head? Are they using inline or are they using batch type systems? There are a number of reasons for that, but the overall answer to your question, Letitia, is that your contract manufacturer is not actually reproducing the shear rate and the mixing conditions you require to stabilize your system that you're doing in the laboratory. There is another workshop I run called the Scaling Up of Emulsion Systems. That's actually covers this topic in depth. Maybe we'll do it again next year, Bridget. I'm not too sure, but if you want to contact me offline, I'm very happy to discuss it further with you. Just give me a shout, give me a call. Probably tomorrow. I'm traveling back to Cape Town this evening, so maybe give me a call tomorrow, and I'll try and help you further.
Perfect. Thank you so much.
Absolute pleasure. Absolute pleasure. Right. That's a good question. Thanks, Letitia. That's a very good example, guys, of a scale-up problem. You know, where in the laboratory everything's fine. You go into production, and it's even more difficult when you go into a third-party production because you don't have eyes on the contractor. And you know, I don't want to be too critical, but you know, there are a lot of contracting companies in South Africa that have got very good intent, but necessarily don't have the right skills to do scale up in the right way. The whole process of taking a laboratory process, for example, we work on a batch size of 600 grams typically in our laboratory. There's a big difference between processing that and processing 5 tons in a factory. And you've got to know what to do to make that scale-up process work. And that's basically the basis of Letitia's question. I'm not surprised she's getting that problem. And I suspect that problem is seen very, very often throughout South Africa and other parts of the world, not just South Africa. I mean, when I worked in the UK, we had a lot of contracting companies there that just didn't get it. And because they didn't formulate the product, they didn't understand what was needed to process it properly. So, but we'll talk more in depth about that another day. Okay, so that's instability. Now let's look at the stabilization of emulsion systems. How do we start to get them stable? And this is really, I guess, the crux of today's webinar is, you know, how do we make these emulsion systems stable? First of all, let's look at the conditions for instability again. So for an emulsion to become unstable, 2 things must occur. Number 1, we must get some sort of collision between the dispersed phase droplets. The only exception to this is creaming and sedimentation, whereas we can get creaming without any collisions. Okay, but for any coalescence or any phase separations, there has to be a collision between dispersed phase particles, and there has to be coalescence. So we're going to separate now phase separation from creaming and sedimentation. We've covered creaming and sedimentation. The way to stabilize against that is to add a rheological modifier, such as xanthan gum, for example. I covered that in some detail this morning earlier on. Now what we're looking at is really what we call phase separation. And this is caused ultimately by coalescence, which sets up a chain reaction, and you end up with complete phase separation. So these are the 2 things that need to happen. So clearly, if we can prevent one of them, we're going to improve the stability of our emulsion system. Let's look at coalescence first of all. Okay, now coalescence, what does it mean? Coalescence begins with the drainage of the films between, or the films of the continuous phase between dispersed phase droplets as they approach each other. So if you bring 2 dispersed phase droplets closer and closer and closer together, there will be a point at which the film between them, the continuous phase film between them, becomes unstable. And at that point, you then start to get coalescence. What happens is, and we'll look at it, we'll look at a diagram in a moment, what happens is, as that film becomes thinner and thinner and thinner, as those dispersed phase droplets approach each other, then there becomes a critical thickness where the film ruptures and breaks. And at that point, which is measured by this equation, which you can see is a function of the film thickness and the viscosity of the continuous phase. That makes sense. Again, the thicker the film, then the more stable it will be, and the more viscous the continuous phase is, because remember that film is continuous phase, then the more stable it will be.
John?
Yes?
Sorry, we have a question from Almira Khan. She's just asking, is it best practice to add the oil phase into the water phase slowly or gradually, or all at once and then homogenize? Does it make a difference?
It's a broad question, and it does depend on the emulsion system, but let me give a general answer. The general answer is you should not add it too quickly, because if you do, you run the risk of shocking the system, and the emulsifier doesn't orientate in the way that it should. So when we're making a 600-gram batch, for example, let's supposing our oil phase is 150 grams, what we will do is we will use a Silverson type mixer. We will typically use a speed of around about 2,500 RPM. This is another important point. That device goes up to around about 9,000 RPM. Don't ever use it at that speed. Never use your Silverson at that speed, because what's going to happen, you're going to create a shear rate in the laboratory you can't create in the factory. So your product may be perfectly stable in the lab. It goes back to Letitia's question. Your product may be perfectly stable in the lab, but you're going to create a processing requirement that no factory is going to be able to reproduce. So what we do is we typically don't go above 3,000 RPM. Yes, we've got a machine that will do 9,000. We never use it, because if we do, we're going to create a manufacturing process that none of our customers can replicate. So going back to the question that you've been asked, so 150 grams into a 600-gram batch, we would switch the Silverson on, make sure that both of your phases are at the right temperature. Please make sure they're both at exactly the same temperature, as close as you can. So typically we use anything between 73 and 78 degrees centigrade. Water phase at 73 to 78, let's say 75. Water phase at 75. Oil phase at 75. Put your Silverson mixer into your water phase. Turn it on, 2,500 RPM, and we would add the 150 grams of oil over around about a minute, about 60 to 90 seconds, making sure that we add some. And then what that does, it gives us the opportunity for the emulsion to form gradually, and then you make the most use of the emulsifier you've got there. You don't want that emulsifier to be ending up anywhere else other than at the interface. That's where you want it to be. That's where it works. So I would say 2,500 to 3,000 RPM. Make sure you've got the right head on your mixer. Okay, I've seen people use disintegration heads. A disintegration head will not work properly for an emulsion. So when you buy your high shear mixer, you should have 2 or 3 heads with it. Make sure you use your emulsifier head. Otherwise, you won't get the most stable system. And then you add it over about a minute to a minute and a half. But don't add it all at once. Don't just throw it in. That does not work. And also don't take it over an hour, because you want to make sure that the temperature is kept up there, and you want to make sure that emulsion forms as quickly as it can, but it must form correctly as well. That should answer the question, hopefully.
Thanks, John.
Okay. All right. So let's look at this then. So let's look at it diagrammatically. They say that a picture is worth 1,000 words. So here we see our 2 oil phase droplets. The distance between them is h. We're moving them together. And there will be a point where the film between the 2 droplets, you can see there, will drain away. It's called film drainage. And when we get film drainage, there's nothing to stabilize the system anymore, and we get coalescence. Okay. And as soon as we get coalescence, what do we end up with? We end up with an oil droplet that's twice as big as the one we originally had. So 2 oil droplets form another oil droplet, which is twice the size or twice the volume. And then that will happen again and again and again. And it's a bit like a virus, it's exponential. So once you start getting coalescence, the chances are your emulsion is not going to make it. Okay, once that coalescence process starts, then ultimately you'll get phase separation. It may take a few days or a few weeks, but ultimately it'll happen. So you've got to try and avoid coalescence completely. That's the first thing you've got to try and do. How do we do that? How do we prevent those collisions? Because we don't want those collisions to take place. Well, there are 2 or 3 ways of doing it. Often we apply electrical charge, and we do that through the use of either anionic or cationic surfactants. Cationic surfactants are not often used except for things like air conditioners, but anionic ones are, and there are some very good anionic emulsifiers around. Sodium stearate, which is made stearic acid and sodium hydroxide, it does work. It's unfortunately susceptible to pH changes, but there are some very good specialized anionic emulsifiers around that work very, very well. And those of you who have worked with those will know they're very, very effective indeed. You've got to be careful with them because sometimes they do suffer from being very sensitive to pH. So if the pH is not correct, you won't get the repulsion you're looking for. And the other thing to do is you can actually use something called mechanical strengthening of the interface. So you're either going to use electrical charge to keep the droplets apart, or you're going to mechanically strengthen the interface. What do I mean by mechanically strengthen the interface? I mean, you're going to use an emulsifier system, which is going to be orientated at the interface, at the oil-water interface. We'll see that in a moment, and that is going to prevent the droplets from coalescing. In fact, what they'll do, they'll bounce apart. So it's a bit like two tennis balls. They'll come into contact, but they won't coalesce. So those are the two basic ways of doing this. If we apply electrical charge, this is what we're doing. There's our oil and water system that we've been talking about for most of the morning. I've chosen oil and water because it's a much simpler system to talk about, but a lot of the discussion points would apply to water and oil. This wouldn't, because electrical stabilization does not apply to water and oil systems, because you don't have a medium, a continuous medium, which enables the charge to be conducted. So this is only for oil and water. And we're trying to make sure that we get mutual repulsion of those droplets, that don't come together. Remember, the two things we're trying to do is, one, ideally eliminate collisions completely. But if we do get collisions, then avoid coalescence. So those are the two things. And there you can see that by using an anionic emulsifier system, the negative charges around the oil droplet there are causing those oil droplets to move away from each other as they approach each other. Remember that, as in with magnetism, with electricity, like charges repel. So a negative charge will repel a negative charge, and that's exactly what's happening with this case. This is called ionization, basically. So what we're doing is we're ionizing our system. We can apply the electrical charge to the dispersed phase droplets in several ways. We can do it by changing the pH. That's not used in cosmetic products very much. It's used a lot in biomedical applications and biochemical applications. Protein chemistry, for example, you can change the system extensively by modifying pH. So if you're working with protein-based materials in biomechanical or biomedical applications, but not necessarily in cosmetic products, what we do is we use adsorption processes, and here we're facilitating the absorption of a charged surfactant at the emulsion interface, and that surfactant will be a cationic or an anionic emulsifier. And the application or absorption of that charge, normally what we do is we add an acid into one phase and a base into the other. I'm using the terms acid and base simplistically. That gives us a salt formation, and that salt formation results in an adsorbed charge. So in other words, if we take this example, which of course is a classic stearic acid with sodium hydroxide, that will form, it will actually obviously hydrate and ionize, and C17H35, that's obviously a 17 carbon chain that will absorb into the oil phase of the emulsion, and the COO negative charge will occupy its place at the surface of the oil phase droplet because it doesn't want to go into the oil phase. And we end up with something like this. So there we can see all of our oil droplets with their negative charges. This would be a classic sodium stearate system. We do have to be careful because there are sodium ions around, because they've got to go somewhere. The sodium ions are dispersed in the system. So we have to be careful that the concentration of those sodium ions doesn't in any way negate the stability, because you can see those positive charges will act against stabilization. So we need to be very, very careful about that. But if we choose our quantities correctly, so for example, if we make sure that our sodium hydroxide is enough to create the anionic system, but doesn't have any excess sodium ions, then we'll get a stable system. There are several weaknesses for this system, the big one being it's very susceptible to pH changes and something called salting out. So, for example, if I was to add sodium chloride to this system, it will become unstable fairly quickly, because the sodium ions would be too high a concentration, and they would negate the stabilizing effect of the ionic charges around the dispersed phase droplets. So this is something we need to be very, very careful about. We tend not to use this at all. We do use anionic emulsifiers, but only specialized ones. We don't use sodium stearate ever at all, unless we get a client who says, I want the cheapest possible option. As long as it's white and it looks like it might be a cream on a good day, then maybe we'll do it. But if a client wants something that looks like it might be a cream on a good day, I tend to try and avoid it completely. I don't really get involved in that stuff anymore. I mean, there's a market out there, but it's not one that we choose to work in. So we choose to work in the high end, as I think most of you know. So that's basically how the system looks when it's formed. And we can look more deeply, because if we see our oil droplet, there's our oil droplet, and we can see our adsorbed negative charges there, and we will get some interaction at the interface. What will happen is we'll get adsorption of positive charges onto the negative charges, and this is something called the Stern layer. So there will be a quantity of positive charges that adsorb onto the interface, forming something called the Stern layer. Luckily, it is not sufficiently powerful to destabilize the system, and then we then get almost like a sandwich effect. That's called the electrical double layer, and then we get a further, and so on. What we're really concerned about is the overall capacity of the electrical double layer. So if the electrical double layer has got a net resultant repulsive effect, then we're going to get a stable emulsion. If the electrical double layer has got a net resultant attractive effect, then we're not. And that's all about keeping the cations as low as possible. So if you're going to use this system, don't just use random quantities of stearic acid and random quantities of sodium hydroxide, because it's not going to work for you. And it is a bit risky. And, again, if you're using, for example, a manufacturing third party, this is a process that's just asking to go wrong. So we tend to try and avoid this. And there are some very, very good cost-effective non-ionic emulsifier systems around now. So we shouldn't really have to use this. But it is used. It's used in very low mass market products where you can't afford anything more. And if it's formulated properly, it can work very, very well. So there's nothing wrong with it, as long as you know what to do with it, basically. And this is called the diffuse layer. So it's the electrical double layer and its overall capacity for attraction and repulsion that we need to worry about. So if we look at repulsive forces on charged particles, so the repulsive forces are the stabilizing forces, and they are provided for by this equation, which looks pretty horrific, especially on a Wednesday morning at +10. I'm not going to go into this equation in detail, but just basically introduce you to the terms. We're trying to keep VR as high as possible. E is the permittivity coefficient of the system. D is the particle diameter. The zeta potential is represented there by the zeta sign. And K is something called the inverse Debye-Huckel length. And as you can see, S is the distance. The important thing here is don't worry too much about the algebraic systems. We're trying to keep VR, basically the repulsive force. We're trying to keep that as basically as high as we can, the force of repulsion. So therefore, you can see the effects that the various components have on it. So again, this is not something you would use in practice, this equation, but it's just nice to sort of see where it comes from. So an emulsion will be stable depending upon the level of counterions present. If there are more counterions than there should be, then the emulsion will become unstable. Additions of low levels of electrolyte, as I've said, will affect emulsion stability, and high levels will cause destabilization completely. So low levels will give you an unstable system, but maybe stable enough to be used. High levels of electrolyte will definitely cause complete destabilization of the emulsion system. And the concentration of electrolyte required to do that is prescribed by something called the Hardy-Schultz rule, which is an inversely proportional ion valency rule. I'm not going to go into that this morning. That's a little bit too in depth for this morning's presentation. So just to summarize then, I'm just looking at the time, we're doing well. Just to summarize then, adsorption as a method of stabilization. So for emulsions, charge adsorption must be effected during the phase processing itself. So in other words, we form that negative charge during the phasing process. It's really sufficient as a sole mechanism for stabilizing emulsion systems. In fact, I would say I would cross out rarely and say invariably sufficient. I don't think I've ever seen a system stabilized with sodium stearate that's good enough by itself. Probably a good exception to that is some very cheap shaving foams, for example. Shaving foams use sodium stearate to stabilize a shaving foam or a shaving cream, for example. If it's a low-cost one, then maybe that's all you need to do. And very often, if we do use this type of stabilization method, we normally use a non-ionic or a polymeric co-emulsifier to co-stabilize the system. So this is only suitable, as I said earlier on, for emulsions with a continuous water phase, because obviously if the continuous phase is oil, then you won't get any repulsion. You can't get electrostatic repulsion in an oil-based system, so only for oil and water systems. Okay, I'm going to cover mechanical strengthening, and now I think we can take a break, a comfort break. But let's look at mechanical strengthening before we do that. And basically, I mentioned there were two methods of stabilization. One was charge repulsion, which we've covered now with the anionic emulsifier systems. We're now going to look at the much more commonly used system, in fact, the most commonly used system, and that's mechanical strengthening. So pretty much all of the non-ionic emulsifier systems we use rely upon this to some degree, either to a large degree or to a significant degree. Some of these systems rely upon a combination of mechanical strengthening and liquid crystal formation, but by and large, mechanical strengthening is the most important method for stabilizing emulsion systems. And there are several ways of doing this. We can use polymers with hydrophilic and hydrophobic character. We can use powders, sometimes with modified surface chemistries to make their surface characteristics different to the bulk of the powder. So you may get a hydrophobic powder with a hydrophilic surface using a surface coating mechanism, and probably most frequently the addition of non-ionic surfactants to achieve maximum interfacial packing densities at the emulsion interfaces. So these are the three basic methods that we use for mechanically strengthening emulsion systems. And they can be used in combination as well. They very often are. Let's look at polymeric stabilization. Okay, so with your rheological modifier, and I picked on xanthan gum and hydroxyethyl cellulose, they do change the characteristics of the rheology in the system, but they do also play a role in emulsion stabilization. So, for example, xanthan gum, not only will it stabilize the rheology of the system, it will also help to stabilize the emulsion itself. Same is true for HEC, although not so much. So these polymers frequently contain a long hydrophobic chain or hydrophobic backbone with hydrophilic side groups, often based on ethylene oxide or glycol chemistries. Not always, but very often that's the case. And the level of stabilization will depend upon the steric effects at the emulsion interface. And what we're trying to do here, we're trying to maximize the so-called packing density. Now, what do I mean by that? Remember that we saw in the first slides that the instability in an emulsion system was caused by the creation of the additional interfacial area between the two phases. And I said that in order to reduce that energy, we've got to try and satisfy that somehow by introducing molecules at that surface. And that's what we're doing now. We're introducing these polymers or non-ionic emulsifier systems, and they will adsorb at those interfaces. And as soon as you get adsorption at the interface, you get energy reduction. And as soon as you get energy reduction, you get stabilization. And of course, the steric effects as well will keep the emulsion droplets from colliding as well. So what we're doing is we're trying to maximize the packing density. And you'll see in a moment exactly how that works from a diagrammatic point of view. So predominantly these are hydrophilic powders, which may also provide thickening. So in practice, a lot of these polymers are hydrophilic or hydrophobic with the hydrophilic side groups, because what we're looking to do really is to make sure there's an attraction at the water phase. At the water phase, so in other words, there's got to be an attraction between the polymer and the water phase. Hence, it's got to be hydrophilic normally, or if it's hydrophobic, it's got to have a hydrophilic side groups to make sure it's associated with the water phase of the oil and water system. So this is a good example. There's my oil and water emulsion. There's my hydrophobic backbone. So what will happen is in this polymer, the backbone does not want to be in the water phase. It's hydrophobic. It doesn't like water. So it aligns itself along the interface at the oil on the oil side. And we then got these hydrophilic side chains, which are orientated into the water phase. Now, I think you can see there, as soon as we apply that polymer to the system, we're in effect reducing the interfacial energy, because that interface, that hemispherical interface, which is the cause of the increased free energy in the system, is being reduced by the application of the polymer, which effectively bridges the interface. It's quite interesting, you know. What we're trying to do here is eliminate as much as possible any energy differences either side of the interface, and by using a polymer stabilizer, that's actually working for us. The additional advantage here is the hydrophilic side chains themselves sterically will prevent collisions of oil phase droplets. So if I bring another oil phase droplet into close contact with this one, I'm going to get some networking and some resistance to coalescence, and that can be seen here. So there's my one droplet, another droplet, and another droplet, and another droplet, and there I'm going to get the hydrophilic polymer chain interaction. So you can see that those four droplets, they can't collide, they can't coalesce, because the hydrophilic chains are in the way. And in fact, what happens as they become closer and closer and closer, those hydrophilic chains, they actually intertwine and cause an even more stable system. So when I see people creating formulations without a rheological modifier or stabilizer, I often wonder, you know, what the rationale is, because it's not impossible. You can do it, but it's pretty difficult to create a really stable emulsion system without some sort of rheological modifier, for example, like this polymer here. So that is what we call polymeric stabilization of emulsion systems, and very, very important, and you know, a very, very useful thing to employ if you're a formulator formulating emulsion systems. The second one is powders. Not so important, but this is important because you need to know what's happening to your powder, because you know your powder will migrate. This is very important for those of you formulating sunscreens with titanium dioxide and zinc oxide, particularly if you're not using predispersed systems. If you are using predispersed systems, you don't have to worry too much about this, because the supplier would have thought about this for you. But there are some companies out there that still do disperse their own TiO2 and zinc oxide. And this can be very important because you can compete for stability. So in other words, if your titanium dioxide is trying to create orientation of one type of emulsion, and the rest of your components are trying to create the interface of another type, then you can actually destabilize your emulsion by adding your sunscreen active. And this is why sometimes sunscreens are very, very difficult to formulate. In fact, they're often very difficult to formulate. So I would say, where you can, if you are using titanium dioxide and zinc oxide, I would recommend that you use the predispersed materials available. There are many. There are many tens for many companies. I'm not going to mention companies' names, obviously, but they're all pretty reliable. Pretty reliable companies. So the point here is that the powder must be very small compared to the dispersed phase droplet size. Oh, sorry, wrong way. And the surface characteristics of the powder must be exhibiting some degree of both hydrophilic and hydrophobic character. Otherwise, the powder is not going to orientate at the interface. So you need to know where the powder is going to go to. And that's quite important when you're doing sunscreen formulation work. Is it in the water phase? Is it in the oil phase? And can it migrate? So, for example, if you're creating a zinc oxide oil and water system, typically your zinc oxide remains in the oil phase where you want it to be. But if you lower your pH below 7, then what will happen is you'll solubilize the zinc and it will migrate into the water phase and do nothing at all for your sunscreen activity. So, things like zinc oxide, for example, in sunscreens are very unstable, especially if the pH is below 7. You need to make sure you get above pH 7 to get the best stability. So you must make sure that the particle surface must not be completely wetted by either oil or water, because if it is, it'll migrate to that phase. So this is how it looks, basically. There are two types. There's a water and oil stabilizer, and it looks like that. And there's, so that's an oil and water stabilizer. It's a hydrophilic powder. And then there is a water and oil stabilizing powder, which looks like this. And that stabilizes water and oil emulsion. So you need to know, for example, what characteristics your powder has. It could be that it only has one characteristic. In other words, it could be all hydrophilic or all hydrophobic, in which case it won't migrate to the interface at all, and you haven't got to worry too much about it. Okay, but you do need to understand. So, for example, things like surface modified silicas is a very good example. If you're using a surface modified silica, you need to think about this type of consideration. And this is what happens basically. So there's our oil and water emulsion with our powder absorbed onto the outside, and you can see that you get some steric repulsion. So as soon as those oil droplets try to come together, the adsorbed powder on the outside of the droplets will prevent coalescence and collision, and therefore stabilize your emulsion through steric repulsion. So this type of emulsion can be stabilized using a hydrophilic powder adsorbed at the interface. If it was a water and oil, then it would be stabilized using a hydrophobic powder at the interface, being on the opposite side, of course, with the hydrophobic character. And lastly, before we take a break, when we're doing perfectly well at the moment, thank goodness. This is debatably the most important part of today's workshop, and that's stabilization with non-ionic surfactants. Now, non-ionic surfactants, there are hundreds. There are hundreds out there. Okay. How you choose the best one is probably a topic for a complete workshop in its own right. So I'm not going to cover that in depth today, but there are some basic things we need to know. Basically, this is the most popular and the most robust method for stabilizing emulsions in the industry. I mean, there are no more frequently used methods than this. And the reason for that, enormous flexibility in formulation, design, and development. There's nothing you really can't do. Wide range of pH, wide range of oil phase, water phase ratios, and the list goes on and on and on. Excellent compatibility with other ingredients. So if you're formulating high-end skincare products, these types of emulsifiers tend not to interfere with active ingredients. So you can actually use the active ingredients with impunity and know you're going to get the right results, as long as you use the right level of active, by the way. And there are a wide range of products, I would say huge range of products commercially available. And the biggest challenge we have as formulators is which ones do we choose? And to be honest, all formulators I know, they've got their own favorites. I mean, we have our own favorites. I'm not going to tell you what they are. That would be unfair to their competitors, but we do have three or four companies that we really think nail this, and mostly with emulsifier blends, which I'll cover after the break, because in the last 10 years, it's been very, very trendy for raw material suppliers not to offer single emulsifier molecules, but to offer blends of emulsifier molecules, which are pre-blended in the right ratio to give best stability. And I'm not one for rejecting that. The old diehards will say no, but that's cheating. You shouldn't cheat. You should do it the right way. No, I'm sorry. In my past life, I was a professional photographer, and I can tell you that when you took light readings from 5 different places on a bride's dress to make sure you got the highlights right without burning them out, it wasn't a very easy task. So these days we use automatic cameras, which are a blessing. So the same is true with emulsifiers. If you can use a blend which works well and has been developed to work well, then please use it and enjoy using it, because there's no medals to be won for doing it the hard way. I've learned that through life. So what's the requirement for non-ionic surfactants? They must have a distinct hydrophilic and hydrophobic character, otherwise they're not going to be emulsifier molecules, and that allows them to migrate to the phase boundary. They must exhibit, I've said solubilities, we should put that into inverted commas because it's not solubilities really, it's affinities, but they must adsorb into both phases, particularly at high temperature extremes. The behavior of a non-ionic surfactant will change with temperature. So you've got to make sure that when the temperature increases to say 40 or 50 degrees centigrade, which is where you're doing your stability, we'll see later on how that works, that it still occupies the interface in the same way. And it must stabilize the dispersed phase droplets through steric repulsion. That's exactly how they work. And if we look at that here, so there we have an emulsion system, an oil and water system. You can see that our non-ionic emulsifier is adsorbed at the interface. The little the red hydrophobic tails clicking inside the oil droplet, the green hydrophilic heads on the outside of the oil droplet, and you can see that there we've got number one, a mechanically strengthened interface, because the emulsifier molecules are occupying the interface, and there we get steric repulsion. So two mechanisms here. One is, first of all, mechanically strengthen the interface to make it stronger. And number two, if the oil droplets do approach each other, then they're going to bounce apart again like tennis balls because of the adsorption of the non-ionic emulsifier at the surface of the molecule. The advantages of this method, they're neutral, so no charge association, so stable in electrolytes. They're very versatile. They're very, very good for freeze-thaw stability. I should have mentioned that the anionic systems I talked about earlier on, they don't work well in freeze-thaw. So if you're going to be marketing to cold countries or countries where the temperature drops below zero, then I'm afraid they're not going to work well for you. Stable to electrolytes. They're available in preformed form. In fact, these days, as I said, they're available in mixtures, which is a nice way to go. They're compatible with other emulsifier types. So you could have, for example, an anionic emulsifier in combination with a non-ionic emulsifier. That is something that people sometimes do. And generally, their safety profiles are good. They're generally non-toxic with a good safety record. Okay, Bridget, I think I think that's a good place to stop. And it's 10:32, so that's pretty good. We're actually halfway through. We're halfway through, if that makes sense. Is 5 minutes enough, Bridget, Dorinda, or 10? What do you want to do?
John, I think let's do 10 minutes. So I think we can just come back at about 22. 22.
Fantastic.
Yeah.
Lovely. Okay,
Perfect.
see you back there then. Thanks a lot.
Thanks.